Hi everybody, today we are learning about the vector and parametric equations of a plane. So we already know the vector and parametric equations of a line, so let's think about what might be different about a plane. Well, a plane is two-dimensional instead of one-dimensional. So think about the fact that with a one-dimensional shape, like a line, we just need one direction vector because really a line just has, it occupies one specific direction in space. But a plane, you need two direction vectors, okay? Because you need to show, you need to give context to the two dimensions. So you need two direction vectors. So we go through on the next page anything that you need to find the equation of a plane, like what's required before you can actually find that equation. But first, let's talk about what the equation of a plane actually is. So planes are flat surfaces. They extend infinitely far in both directions. And we use parallelograms to designate planes. And they're actually designated by pi, okay? So it's just like we use L to talk about lines, we use pi to talk about planes, to label planes. That's just how it works. So let's talk about this. So here is a picture of a plane, this parallelogram, and we have two vectors, A and B. And we have a point on the line that we're given, which we'll call P sub O. All right, so A and B can be translated anywhere in R3, but we're going to put them tail to tail here so that they define this plane. So there is vector A, and there is vector B, okay? And when they're shown tail to tail, they can represent infinite number of parallel planes, but only one of those planes will contain the point PO. And that's the point that kind of determines where they are in 3 space. So remember, vectors are translatable, so but only one of these planes contains PO. So this here is the point PO. So we're going to call this blue vector RO. Okay, and then what we're going to do is represent P, some other point on the plane, okay? And that just represents any point on the plane, okay? So we can draw a vector R. Hopefully we can draw a vector R, kind of. There, and then we can connect PO to P. Get a different color here. All right. So A and B can be anywhere in R3, but when they're placed tail to tail, they form okay, I said that. The parallel represents the plane pi. Parallelogram represents the plane pi, and it contains A, B, and PO. So we're going to let RO represent the point PO, and R represent any point P on the plane, any other point other than our given point PO. So then we can say that the vector from PO to P is a linear combination of A and B. Okay, because A and B create the plane essentially. Remember that the linear combination of two vectors can represent any other vector on the plane. So we can say that PO to P can be written as some linear combination of A and B. So we say SA plus TB, where S and T are two different parameters. Okay, so this is just a linear combination of A and B. So therefore, we can also think that using the triangle law in this triangle here, RO, POP, and R, we can also say that OP, so that means any point on the plane, is equal to OPO plus, plus POP. So any point on the plane R is the addition of the vector that's represented by the point we know plus the vector from that point we know to any point on the plane. So therefore, based on this, what we can conclude is that R is equal to RO, our known point, so that's just the same as this. OPO is the same as RO, plus SA plus TB, which is equivalent to this, where S and T are in the set of real numbers. So really, this is quite similar to the equation of a line. It's just that we have two direction vectors here instead of one. So RO represents a known point. And these two represent two direction vectors. And then we have two different parameters here. Okay, so then the parametric equations are x equals xo plus sa1 plus tb1, y equals yo plus sa2 plus tb2, and z equals zo plus sa3 plus tb3. Okay, so each of the x coordinates, the y coordinates, and the z coordinates, and then we also include the s and t are in the set of real numbers to indicate that they are scalars. Okay, so think about it. The fact that it's two-dimensional means that those two dimensions need to be represented by two direction vectors. Okay, that should make sense to you, that a two-dimensional figure needs two direction vectors to give it its shape. Okay, so to create the equation of a plane, like I said, we just need two direction vectors, and therefore create, okay, I'm repeating myself, but just really want to make sure you get this point. Okay, so a unique plane can be determined. There's four different ways, four different sets of information. That is enough to give us a complete equation of a plane. So for each one of these, I'll just create a quick parallelogram just to illustrate what's going on. So if you have a line that you know is on the plane, okay, we'll call that L, and then any point not on the plane, we'll call it PO. How does this work? Well, if you know the line, then that gives you one direction vector. And then to find the second direction vector, you just need to find the position vector between a point on the line and the point that you're given. Okay, so the second direction vector is found by finding the position vector from a point on L to the point that you know. Okay, there'll be an example about this in a minute. Okay, the next way that you can find the equation of a plane is if you're given three non-collinear points that are all on the plane. So let's call it, let's say A, B, and C. So if you're given three non-collinear points that are all on the plane, you can find the two direction vectors, AB to AC, and then just use any of the 3 points as the point. Okay, so I guess you can write that there if you want. So direction vector would be here AB and AC, and then you'd use any of the points for RO. Okay, another option is two intersecting lines that are on the plane. So here would be L1, and here would be L2. So the two direction vectors would already be given to you through the vector equations of these lines, and then you could choose any points. So that one's quite simple. And then the last option is two parallel but non-coincident lines. So here's L1 and here's L2. So one of the direction vectors would be the one that was common between the two parallel lines, okay? They would have the same direction vector, or at least collinear direction vectors, because they are parallel and in R3. And then think about, how could you find the second direction vector? Remember that the vector equation of each line will also contain a point. So the second direction vector can be found by finding the position vector between the 2 points that are given to you. Okay. All right, so let's do some examples, and hopefully this helps clear up any confusion you might have at this point. So here's a plane. It contains these 3 points. So recall that we need 2 direction vectors and a point. So obviously we have 3 points, and actually we can choose any of those 3 as our point, but we need to create 2 direction vectors first. So we'll start with vector AB, and remember that that's just OB minus OA. So that would be -1, in this case +1, 1 minus 3, and 0 minus 8. So that gives us the direction vector 0, 1, 4. And then our second direction vector can be BC. So that's C minus B. So 4 plus 1, 1 minus 1, 1 minus 0, and that gives us the direction vector 5, 0, 1. So now we know that we have our R. Now I can use any of the 3 points as my RO. So I just use the first one, doesn't matter, -1, 3, 8. That's a known coordinate. And then I set up my parameters plus S and use my 2 direction vectors. So 0, 1, 4 plus T, 5, 0, 1. And then S and T are in the set of all real numbers. Again, this is to communicate that S and T are scalars. All right, so do either of these points lie on the plane? Well, what we need to do is set up the parametric equations. Okay, so X is equal to -1 plus 0S. So I don't actually need to put that. So plus 5T. And then Y is equal to 3 plus S, and then 0T. And then Z is equal to 8 plus 4S plus T. Okay, so we're going to take those parametric equations and we're going to set them equal to P. Okay, so I'm going to set my -1 plus 5T equal to 14. I believe it is, yeah, 14. And my 3 plus S equal to 1. And finally, my 8 plus 4S plus T equal to 3. So notice that for these two, I can actually solve. In this case, I can solve that T equals 3. And in this case, I can solve that S is equal to -2. So the question now is, if I put in a T of 3 and an S of -2 into the Z parametric equation, will left side equal right side? Okay, so I'll change the color here and add that commentary. So you check, here, I'll write that here. Check if S equals -2, T equals 3 works in equation 3. So this equation. So 8 plus 4 times -2 plus 3 actually does equal 3. So yes, so therefore P is on the plane. Okay, so you can repeat the process for Q. And if you do that, you get 14 equals -1 plus 5t. So same as before. So this also results that t equals 3. And then you get that 1 equals 3 plus s. So again, s is equal to -2. So if you take your last one, though, 5, it equals 8. And so I'm going to sub in my -2. So 4 times -2 plus 3. That does not work. Okay, you'll get that left side does not equal right side. So therefore, Q is not on the plane. Okay. So again, anytime you're asked to prove if a point is on a line or a point is on a plane, set up the parametric equations, and that will allow you to find your answer. So in example 2 now, we have the equation of the plane given to us. So a plane pi has the equation r equals 6, -2, -3. So remember, this means that it contains this point. So the point 6, -2, -3 is on the plane. And it has these two direction vectors, 1, 3, 0, and 2, 2, -1. All right, so determine the point of intersection between pi and the z-axis. So the z-axis occurs, sorry, I lost my pencil here. The z-axis occurs when x and y are both 0 and c is some value. So we're going to substitute x equals 0 and y equals 0 into the parametric equations to find the s and t that give those solutions. And once we know the s and the t that work for that, then we can use that s and t to find c. So our x parametric equation is 6 plus s plus 2t. Okay, so we're going to set that equal to 0. So 6 plus s plus 2t equals 0. And then our y parametric equation is -2 plus 3s plus 2t. So we can set that equal to 0 as well. Again, this is because x and y equals 0 at the z-axis. So notice that we can do substitution here because 2t and 2t, if we subtract the two equations from each other, that will be eliminated. So 6 minus -2 is 8. S minus 3s is -2s. These eliminate, which is what we are requiring. And 0 minus 0 is 0. So then we can solve this to find that s equals 4. Okay, so we can put that back into either of the equations. So for example, 6 plus 4 plus 2t equals 0, and solve to find that t equals -5. So now we just put these parameters into the z parametric equation, which is -3 plus 0s minus t. So in fact, the s didn't matter here, but we didn't know that. So we'll put in -3 minus -5, which gives us +2. So therefore, pi cuts the z-axis at 0, 0, 2. All right. Final example. Okay, in this case, we're being asked to determine the vector and parametric equations of a plane containing this point and this line. So these are both on the plane. So remember that this here is a direction vector. So that is one direction vector that we already know is on the plane. Yay, we have one. But we need to find a second direction vector since it is a two-dimensional object. So second direction, vector. So we do that by finding the vector between P and the known point on the line. Okay, that will give a second direction vector. So we use 2 given points. So for notational purposes, we'll say let capital A be 1, 1, 1. So we can say then that AP is the second direction vector. So it's 1 minus 1, minus 5 minus 1, 9 minus 1. So that gives us 0, negative 6, 8. So remember that direction vectors are collinear. So we can simplify this to, it's a simpler form. We can simplify it to 0, positive 3, negative 4 to make a simpler, excuse me, collinear direction vector. So now we have our 2 direction vectors. The first one is from our given line. The second one is the one we just created. And now we just need 1 point. So we can use either point that's given, 1, 1, 1, or point P. So I'll use 1, 1, 1 just because, it's simpler. That's point 1, 1, 1. And then our parameter S and our first direction vector, negative 1, 1, 0, plus T, 0, 3, negative 4. And don't ever forget to write S and T are in the set of all real numbers. Okay, so as a result of this video and these learning points, you should be able to create the equation of a plane if you're given 2 intersecting lines, 3 points, a line and a point not on the line, and then 2 parallel or non-coincident lines. So basically any of those 4 situations I presented to you, when given any of them, you should be able to create the equation of a plane. You should also be able to determine if a given point is on the plane if you know the vector or parametric equations. Okay, so thanks for watching, guys. I hope you learned lots.